systems. Okay, so data models, look at it in terms of a representation of reality. That's a model. A model is a representation of reality. So if you take something like those beauty models or fashion, those who do the modeling, you realize that they wear a dress, someone sews a dress, a certain style, then they model it. In other words, they are telling you that when you wear that dress, that's how you're going to look like. Okay, computer models are also like that. The idea is to represent something that is real, but in the digital environment. Okay, so GIS data models try to actually model what is on the ground. What is on the ground? Okay, so there are two data models in GIS that we need to know. But then to even start with, we can say data structure. Okay, so data models and data structures are related in a way. Okay, if you say data structures, at this level, I'm going to forgive you. Data models, I'm going to forgive you. Okay, but I prefer data models. Is that okay? The difference is in implementation. Okay, all right. So within the computer, how the data models are really structured, how they are stored, that will be the structure. The model is the concept. Okay, the idea. All right. So there are two data models that we are going to talk about. Okay. In fact, you can talk about the topological model, the network model. They can talk about the vector, but I think basically we can reduce even the network model into the vector model, and then we can also talk about the raster data structure or raster data model. Okay, so I will expect you to know just two things: the raster and then the vector data model. So in GIS, talk about raster and then the vector data model. So 1, 2, and then you are good to go. Okay, so what is the raster data model? What is it about? The raster data model, without even referring to the slide, I just want you to know that it touches on a picture. Think about a picture. Are you okay? So pictures are example of raster model, implementation of raster model. Why? Because every picture is made up of what we call the pixel. Is that okay? So the pixel is like the smallest unit of representation in the raster model. So an area is subdivided or tessellated into grid squares, and then the grid squares, every single square now stores one particular color value. Okay, so can you imagine if we're storing 1, 2, 0, 1, 1, and then each value, okay, that we've stored represents the attribute at that location. Okay, so look behind these squares and then the values within them, and then see that behind it is reality. So what we are actually, the squares that we put there are only representing something that's happening on the ground. Okay, so then the question will be, so say, what does the picture, you mentioned picture. Pixel stands for picture element. Okay, so in other words, the PI you see here is for picture, and then the L here is the elements. Okay, so to understand the raster data model, then you need to actually look at a set of squares, so many of them. All right, so we have like devices that are able to capture data in that structured that way. In other words, the raster data structure is actually derived or obtained using cameras. For example, cameras are like sensors, but there are different types of cameras. We have scanners and all that are mounted on satellites that allow you to actually scan the ground or the area of interest, and then to extract these values. So let me just say that anytime, if you've taken a picture today, which I have today, I've taken, I don't know, I like just using my camera. At a point I was at the mechanic shop, no, at the vulcanizer shop. Okay, the guys who fix the tie. And then I had to use my camera. I just felt, let me just take a shot of myself, a selfie, and see how the mask is looking on my face. And when you do that, you simply divide yourself, your face, into squares. That is what we are talking about in the raster model, nothing else. Okay, so the raster data model is like that. Let's go back and look at the lecture slide, because the whole idea is to bring understanding. Space is subdivided into regular grid squares. Space. So space, panoramic space, geographic space, okay, environmental space, whatever space that you have around you, your environment, yeah, you can, it is subdivided. Concepts, the raster data structure, make sure that the space is subdivided into regular grids or square grid cells. I mean, it's like tautology we have over here. Yeah, but basically that is what the raster data structure does. And we shouldn't limit ourselves to that, because you could have other forms of polygonal meshes. Are you okay? A mesh. So you can imagine if you subdivide space into regular grids, then you are going to have something like a mesh. Are you okay? Like what I showed you on the other side. Yeah, you could have like a grids really. Oh, what happened to my marker? Don't start this now. Okay, so you can have like lines. Okay, hold on a second. You can have divide space, but then if you divide space, you should have squares. So these are squares. So this one is a square, that's another square, that's another one. Okay, once you divide the area, so there could be a river going through. Okay, there could be some feature, somewhere in there, and then all you want to do is to model it as what, using the squares. Is all right. It is possible to do that. It's possible. So we just, anywhere you see this yellow thing, then you record a value there. Are you okay? Everywhere you see the yellow thing, you record a value. Are you okay? And then when you do that, then you have what the normal people call picture. Are you okay? Anytime you're taking a picture, you are actually creating a raster data model. Are you okay? Anytime a satellite, you get a satellite imagery, it's a raster data. It's a raster data set, and it's based on the raster data structure and raster data model. Is that okay? So going back to your slide then again. Yeah. So instead of us using squares, we could have used what, other polygonal meshes. That what we really mean is that you don't have to use a square, you could use a triangle. Are you okay? In fact, triangles are used in what we call the triangulated irregular network. We talk about them, the 10 model. Are you okay? All right. Now, so fundamentally, there are a few things that we need to understand in the raster data model. The first one is that the location of each cell is defined by its row and column numbers. Is that okay? The location of each cell, so the cells are the squares, okay? The squares are the cells, and then the location of each cell is defined by the row and column numbers. Okay, so in other words, we can decide that this is 1, this is row 1, column 3, column 4, and then this is row 1, row 2, row 3. What it means is that I now have a matrix. Okay, I have a matrix, and in the matrix, I can identify every square by the row and then the column numbers. So example is, if I pick this one, this particular cell here, okay, so this cell is actually defined by what? Column 2, row 2. So you have a matrix. Are you okay? A matrix made up of what? A regular gray squares. Are you okay? Regular gray squares. Okay, Tofik, you joined us. So let me just Take note of that. Tofik just joined us. I mean, I'm taking these things seriously. Attendance. Okay, so now, we can define every single square that's defining, every single square in the squares, the gray squares, by their row and column number as in a matrix. Okay, all right. So let's go back to our slide again. All right. Now the area that each cell represents defines the spatial resolution of the data. In other words, spatial resolution has got something to do with the accuracy with which we are representing, the object. Are you okay? That is spatial resolution. Is that okay? We can also have what we call spectral resolution. So in the remote sensing data acquisition using remote sensing, remember I touched on spatial resolution, which is actually defined by how well an object is represented. Are you okay? Okay, how accurate. If we can distinguish between objects, then we are talking about resolution. Is that okay? It's got something to do with the eye, actually the eye's ability to see something. All right. So spatial resolution is got to do with the distinctiveness. Are you okay? Being able to distinguish between objects. Okay. So we can have, for example, a satellite imagery of, say, I'm going to give you a typical resolution, say 1 meter resolution satellite imagery. So 1 meter resolution satellite imagery is actually, what does it mean? It means that the squares that were captured on the ground when the satellite was passing over the area, the squares were 1 meter by 1 meter. Is that okay? All right. So in that case, then every object that falls into a square of 1 meter by 1 meter, okay, is going to be generalized. There's some kind of generalization that goes on. Are you okay? So every object that falls anywhere here is going to be generalized. So if it's water, if we find water around this square, we are going to generalize and call the square water. Okay, so there's some inaccuracy with the representation using satellites, the raster data model. Are you okay? Because the area that each cell represents defines the spatial resolution of the data. Not only that, we will find out that there's a generalization that is done. We generalize. Is that okay? We look into the squares and say, what is here? Okay, we find some water. Okay, decide what you think we find in that square. And we're going to say, okay, we think it's water. Are you okay? So the area that each cell represents defines the spatial resolution of the data. So now the spatial resolution for our imagery in question is 1 meter, 1 meter resolution. Normally we use, because we are using squares, we only mention 1 meter resolution satellite imagery. We don't say 1 meter by 2 meter. Okay, because we are not using rectangles here. All right, so let's move on and look at other characteristics of the raster data structure. The position of a geographic feature is only recorded to the nearest pixel. This is what I was talking about. Okay, so that if I find something, yes,
considering the squares,
yes,
granting that the dimensions want to take the form of triangles, that the triangle identification model. I want to know whether the triangles would also be the way we have.
I'm listening to you. Go ahead.
The squares. I want to know whether the
triangulated irregular network normally make use of the intersection of well-formed triangles. Okay, so you are now bringing a new topic. So I hope you are ready. So you understand that. So we are saying that let's not forget that it's possible to use other polygonal meshes such as, say, triangles. Are you okay? And yet, if you want to pay attention to that one more, then you may lose track of this one. because then I'll start talking about that one, which is a triangulated irregular network, which is a whole model on its own. I think I have to just say that at this point. And that is what is used for some of the cartoons that came, freedom fighters cartoons, IOK, grand auto theft and all those ones, you know. At a point you could almost see the triangles that were being used to form it. But the focus is not on that. The focus for this one is to look at the squares, regular gray squares. Understand that first, then go on and look at the triangulated irregular network. I hope you're with me.
Yes, sir, I'm okay.
Yes.
Yeah.
So
Thank you, sir.
yes. So the triangle, we are saying that it's possible to look at other ones, but let's look at this particular one for now. So the square, every square, if you find water, say this is a river, okay, the line, the red line is a river. If you find water in this particular square, then what we do is that, so this square here contains water, okay. Then we assume that this whole square is water. That is how the raster data model works. In other words, if someone takes a camera and is taking a picture of you, it divides you into squares and then associates single values with the squares. Is that all right? So that if the camera now finds that, okay, it's storing just colors. Okay, so every area where it finds the color, I'm using the camera that we take, you know, the selfies that we've been taking, because that, you can relate to that. But we are interested in engineering. We are interested in the camera mounted on
Fine,
a
madam.
say a plane, are you okay, or a satellite, and it's looking down on the earth. That's why we are interested in engineering. We are not interested in selfies. But I'm just thinking you understand it easier. It's easier for you to understand if I go with the selfies. Are you okay? All right. So it will divide. If you take a selfie using your phone, point at yourself like that, they will divide your face into squares, regular squares, millions of them. Are you okay? Then every single one of them will now store a value for the part of your face where the grid is. So you can imagine my face covered with a grid. Anytime you're taking a picture, take it out, or someone to take a picture of it, it's divided up into square grids. Okay, now the position of the geographic feature is only recorded to the nearest pixel. We've talked about that. The value stored for each cell indicates the type of object. So in other words, if my cheek is fairer than my nose, which, you know, shouldn't be the case, okay, then it should record a lighter value and a darker value on my nose. That is what's going to happen. When a camera or a sensor is mounted on a helicopter or a plane, when it looks down, whatever it sees, if it's recording true value, then the squares will now be picking values that it finds within every single square. Okay, that's what we're talking about. The value stored for each cell indicates the type of object, phenomenon, or the condition that is found in that particular location. Is that okay? So we're talking about the position of geographic features. We're talking about the location of each cell, which is inferred by row and column numbers. Are you okay? And then here we are giving examples of the kind of values that we want to store in the raster data model. So we can store integers, real numbers, alphabets, but often we want to use integers, okay, in what we call a lookup table. It's also created. We create something called a lookup table to tell us that, okay, if I see number 1, what is it? Okay, so it's able to tell you, if you see 1, you are seeing bare soil. If you see 2, you are seeing something else. Are you with me? So there should be a way to track. Are you okay? All right. Different attributes at the same cell location are stored as separate themes and layers. This one we don't need to talk about. We've already done themes and layers. So I believe everyone in the class understands the concept of themes and layers, and they can be applied in the raster data structure or raster data model. Are you okay? All right. So that we should even be talking about that. It's easy for us because we've already done it. Okay, so now I'm going to show you another diagram. So if you didn't really get what I was talking about, look at this one carefully. Everything is in this. There's a Chinese adage that goes like, a picture is worth 1,000 words. Are you okay? A picture. So I'm showing you a picture. everything I'm saying, this is what I'm saying. Columns, rows, are you okay? Defining the coordinates of a cell. Now you can see that the cells, the blue cells are defining a particular, particular thing or phenomenon or object. Now the value 1, 2, 3 are actually indicating the kind of value. So the color values will be mapped to actual integer values. Are you okay? The colors are just to help us to visualize. All right. Different themes or layers. You see the way we've done it in concept. I think when I was teaching that topic, I also drew several, rectangles. I don't know how I did it, but I had a way of showing you that we can separate data into different. So you can have one layer for, say, temperature, next layer for soil acidity, next layer for slope. Yeah, you will find out that we can actually store slope values. Are you okay? We can find out that. So here, this is the lookup table. The lookup table is telling us what we are looking at the corner. So 1, we have a forest. 2, we have cultivated field. So now we have a way of like understanding what the values in the raster model stand for, what they are. Okay, so we've already talked about this, separate themes or layers. We've also talked about several variants to the regular grid raster data structure, which is really the triangulated irregular network. It's an example. Okay. So this is an irregular tessellation. There's regular grid squares are regular tessellation. So to tessellate is to just cover an area. To tessellate is just cover. Are you okay? It's an English word. We can just look out for it. We can also have a hierarchical tessellation. Quad 3, of course, please ignore this one. It's all right. It's a whole topic on this one that I don't want to talk about now, given the scope. It's all right. So triangular irregular network. So here, this is what I was talking about. This is actually being used to create cartoons and surfaces, and you see the cartoon walking around on that thing and you think it's real, don't you? That's the power of the triangular irregular network or triangulated irregular network. It depends on how you look at it. All right, so there we go. All right, as opposed to the raster data model making use of all these squares and all that, we have the other model called the vector data model. So the raster model data model is not Bob Marley. Is that okay? Don't go and write raster. Learn how to spell the word raster. It's not Bob Marley. Vector data model, on the other hand, simple, very easy to understand. Points, lines, and polygons make up the vector data model. So the points, which objects on the earth can be represented as points? Then you go ahead and then you just say wells. Okay. You go and find all the, you go and look for a well, and then get their coordinates, the XY coordinates, and then that will be plotted as a point and can be symbolized as well in a certain way. The lines, they say, okay, I'll go for railway. Is that okay? So so these are examples. So there are a lot of them, loads of them, objects that can be represented. Then you go for polygons. I want to go for farm because my dad is a chief farmer. No, he's not a chief farmer. So farm. So my farm can be represented as a polygon. That is all there is to the vector data model. So there are real world objects. In fact, any object can be modeled as a point, a line, or polygon according to the vector data model. Is that all right? And I think AutoCAD also makes use of that. Is that okay? Now is here. Took him so long. So let me record your attendance.
Yes, good afternoon.
Good afternoon. How are you? All right. Okay, so let's go for it. Yep. So wells for points, railways for lines, farm for, so I can ask the class to actually produce more of these. So wells is just one example. I want you to give me 5 more. You should be able to do that. Is that okay? give me 5 more objects that can be written as lines. You should be able to think outside the box. I told you that geographic information systems means that objects around us and how we are representing them in the computer, and then of course to support the decision making. You can give so many objects that can be written as polygons without talking about a farm. We can give more than say 100 examples. Okay, so get ready. When I ask you, don't forget that I told you that you can have so many of them. Okay, so points, lines, polygons from the fundamental geographic pyramid. It doesn't matter. Forget about all that. Sometimes I put all sort of stuff in my presentation. All right, so if you don't know how a point looks like, that's how a point looks like. Okay. All right, so points. Then you can join 2 points to get a line. Then you have a linear object. Then you can also join the linear objects and close them. Then you get a polygon. All right. So here are a couple of polygons that have been, joined together that are sharing common boundaries. And then we can store the points within the computer in a tabular form. Okay, so we can say that, okay, the point number, give me the x coordinate, the y coordinate, call it point 1, and then also have another table related to it, join it to it in such a way that when I see 1, I know the coordinate is 7, 6, and then the attribute there is that that point is 12.35 deep, 12.35 units deep, and then there's an amount of something else that I can measure at that point, 63.45. Are you okay? All right, so if you were working on a mining site and you were actually taking, say, soil samples, then you could be talking about some values, certain values, then it become more relevant to you. Okay, so this is how points are stored within the computer in tabular form. Obviously, on the left-hand side, this is what you want to call a map. Are you okay? This is a map. And so, yeah, I'm not mentioning it, but in this, guys, the graphical representation of objects is really the map. Are you okay? We shouldn't run away from that. It's the way to go. Using maps to represent phenomenon is the ideal thing. All right. Okay, great. So lines here, we can see the beginning and end node of the line. When this, attention please, when this Zoom meeting ends, let's use the same link and come back again like we always do and continue from there. We have 10 minutes to finish this one. Each line is stored by the sequence of first and last point together with the associated attribute of this line. So here, look at it, look at point 1. That's the node 1, okay, node 1. And line A is actually made up of node 1 and then node 3. And then when we talk about the line A, we can also associate what certain attributes to it. Okay, so this is how, this is, in fact, in GIS, we call it the attribute table. And I'll show you in the practical, I'll show you. You open it up and then you can see the objects and then how they are storing their values, their attribute values in a table. So similarly, you can imagine that the polygon will store nodes, okay, and then every polygon should have some attributes that can be stored with it, which actually means that I can have more polygons, okay, I can have more polygons. That will now, so polygon A, if this were polygon B, then I could now continue from here and write B, give it some values, okay, and then on and on. I can have so many of them in one layer. Okay, so that is the idea of storing of vector data in GIS, or that is what the vector data is about. Okay, so let's see if we can talk about more. All right, so yes, we can talk about other implementations, but please do not bother yourself so much. We can have what we call the spaghetti vector data model, hierarchical vector data model. Per this class, I wouldn't bother your head about other variants to the vector data model. I want you to just be able to tell me and describe to me what the vector data model is and how we can actually relate it to objects on the ground. Are you okay? All right. All right, so I think a few, narratives here, a few things to note. it stores adjacency information because vector data is actually, topology is only relevant in using vector data structure. Remember we said topology has got to do relationship between what geographic features. So we can only talk about topology. Adjacency is got to do with topology. Yeah, adjacency is got to do with topology. All right. Okay, so what are these? Is each individual line segment is defined by coordinates of its endpoint. I think we talked about this. Nodes, topological information is stored by recording from node to node. I think we've seen all that. Left polygon, right polygon for contiguity. Are you okay? Remember that. So we are virtually kind of touching on another topic that we've actually handled last week or so. Are you okay? And that's topology. And I told you even then that I'll be talking about vector, and then vector and topology, they relate because topology make use of the vector data structure, vector data model. It's only relevant in the vector data model. Are you okay? All right, so yeah, ignore this one, spaghetti data model. I don't intend to talk about this in this class. Hierarchical vector data model. I don't intend to talk about this in this class. Okay, more of that. Okay, so you can ignore that. Those who didn't come for the lecture, they can read that one. Are you okay? Hello, mommy. Pacho Debbie. Please hold on. Please hold on. Please hold on. Class, hold on for a second. My neighbor, I think, is asking some to finish this. So here, I'm trying to emphasize more on the relationship between the vector and the raster model. And we are going to also look at the advantages of vector, versus the raster. Is that okay? So clearly it's the same area, okay? And then the one on the left is, okay, let me ask someone to say it. Anybody, Israel, or I don't know, Nanaya, or anybody at all. Which one is vector? Which one is raster? Which one is vector? PQ. Which one is vector? Which one is raster? And why?
Hello.
Hi, go ahead.
So the P is the vector and the Q is the raster.
Why?
Yes, the vector talks about the connection between two nodes.
Okay. Vector.
And we are seeing that the connection between the two nodes. And we are seeing that in the P.
Vector. Hold on. I think I like your submission, but let me make something clear. Vector is made up of lines, points, lines, and polygons. And then you can see that the P is made up of what?
We can see that the P is having the connection is having
no, the P is made up
points.
of polygons. It's made up of polygons.
Polygons. Okay.
Yes. That's it.
So I was thinking. Hello.
Yeah, go ahead.
Yeah, from what I deduced, I noticed that with the vector,
yes,
when the vector utilizes two or more points to form the lines and the polygons.
Yeah, the basic. The basic. Yeah, I understand you. The basic, the fundamental geographic primitive, like the basics of the vector is points. Everything is points. As you're saying, yes. But what we are looking at here is actually polygons. We all know that the polygon is made up of lines, the line is made up of points. But the question was that what makes this one like the P, the vector? So the answer is that it's made up of polygons. End of story. So you don't need to go any deeper than that. So you are really kind of showing that you really understand the topic. But then in doing that, you are getting the answer wrong. Okay, but it's good. It's good. Yes. Okay. So I've just drawn something here using the pink pen. Nanayao, I want to hear from Nanayao. What I've just drawn here using the ink pen. What is it? What model is it? And why? And explain to me, justify what model. Is it raster or vector and why? Nanaya, if you are listening to me. Okay, if Nanaya is not listening to me, Sobalt, right, or Tafik, any of you can go ahead and tell me what model is what I've just done on the right side. Yes.
So I think this that you have drawn is a vector.
It's vector
model.
And why?
Yes, sir.
And why?
Yeah, because we can see lines and points in it.
Okay. So we can have we have lines, interconnected lines, definitely.
Yes.
Okay, great, beautiful. So on the right hand side, we have the raster representation of something. These could be fields or they could be anything at all that you can think about. What we have here on the P, okay, on the ground, it could be something, a field of corn and water and all that going on. So what the raster is doing is that it's actually representing everything that we are seeing. The polygon A is being represented by the values that we found on the ground. Polygon B, the same thing, but we can see that there is a problem, isn't it? It's not able to, the raster is not able to keep the shape very well. It's only kind of accurate to the size of the squares that are being used. Okay, so there is some kind of disadvantage using the raster, but at the same time, the vector 2 could miss something, because what if there is, other things going on in here that, we couldn't capture. There's some generalization going on with the raster, but the generalization with the vector is even worse. Are you okay? It's even worse. Here we are saying everywhere here is probably grass. Let me give an example.